Um, I so I'm not sure yet. I haven't made a decision about that. I suppose I could. Let me think through which ones I would want to give. What I may end up doing is giving you an exam from when I would have taught this before at Penn State. Oh, we did quizzes then. We did quizzes every 2 weeks instead of midterms. I'll think about something. We'll come up with a plan. A couple of things though to note. I did forget to mention that next Friday, not this Friday, so a week, the end of next week, we will post all of the solutions to the homework problems you've been working. So you'll have those to work from for studying. Please note that the exact numbers that you used for the written problems, they should be exact, right? But for any of the problems that come from the Wiley materials, you may have had a different set of numbers than the solution. So you've probably identified that already if you've looked at any of the solutions after you solve a problem. Sometimes they'll say, well, you should have done it this way, and it's a totally different set of numbers, and that's quite common for Wiley. So that's just a heads up. But yeah, I'll work on posting something for you all. And so when will it be posted? I'll aim for next Thursday at the latest. So let me try to get that worked out.
Professor, I had a question.
Yep.
So when is the specific time for the midterm on Tuesday?
So we're just going to use class time to do it. So
okay,
so it'll be the normal class.
Okay, and we'll be having an hour and 15 minutes for the midterm.
Yep, that will be no problem.
Okay.
This was the one you did, right?
Okay.
Did you get the green
Anyone else? All right. Terrific. Okay, let's go ahead and start progressing through this. There's my cursor. Okay, cool. Okay, so in the past couple of weeks, or maybe I guess the past week, we've talked about dealing with the sum of moments analysis. In particular, in a case like this, on the left-hand side, we have a gate on this sloping wall that has some kind of a shaft to it, or some axis of rotation. And if we take the moments or sum the moments about that point, for example, we concluded a couple of things. We concluded, one, we found out, let me get my pen started. We concluded, number one, that FR does not, sorry, I'll get back to my capital letters, does not act at the centroid. Right? We still use the centroid of the shape, in this case of this particular gate, whatever shape it is. We will still use that to figure out what all the pressures are that will add up. But FR itself, because pressure is increasing with depth, will not act at the centroid. And that's because the pressure down here is less than the pressure up here, right? There's some gradient that occurs because those are different depths. So number one, the resultant force does not act at the centroid. And number two, then, just to formalize what I just said, but we still use depth of the centroid. Oops. To figure out the pressure. Okay, and remember, depths are all of these H's on this side, and these Y's are measured from the outside. They're a length along the outside of the body that we care about in this case. Okay. One thing I forgot to get going was our eye clicker, but I'll do that in a moment. Oops, didn't seem to work. Okay, so this is one of the problems that we would have worked yesterday that we ran out of time for. So I wanted to spend a little bit of time on this because this is now a case where we have two forces acting on one gate. So you can see that there's water on the left-hand side and gasoline on the right-hand side. Note also that the gate essentially goes, I don't know if you guys can see my cursor really well. It's this red vertical line, and it's got a little stop here, and then there's a partition above that. So the only thing that can move is the gate, and the gate can only really move to the right. It can't move to the left because of this stop that's here, okay? And so let's read the problem statement. An open tank has a vertical partition, and on one side contains gasoline with a density of 700 kilograms per cubic meter. Is that greater than or less than water? Our typical number for water.
Less than?
Correct, right? We've been using 1,000 or 998. Somewhere close to 1,000 is what we would have for water. Good. Okay, at a depth of 4 meters, as shown in the figure, a rectangular gate that is 4 meters high and 2 meters wide. So the 2 meters is going into the page here. 4 meters high is the dimension we're seeing here. And hinged at one end is located in the partition. Water is slowly added to the empty side of the tank, so the left-hand side. And the question is, at what depth H will the gate start to open? In other words, how high do we have to add water until the gate starts to open up and we end up mixing our water and our gasoline, essentially? All right, let's see. So a couple of things. Number one is that we know that the density of water is about is 1,000 kilograms per cubic meter, and the density for gasoline we're given here is 700 kilograms per cubic meter. This H1, it's drawn to be somewhat generic here, but because of the way this is drawn, we know that this is 4 meters. Okay, we're given that the gate is 4 meters tall, so and the gasoline is drawn to completely sort of occupy the right-hand side of the full height of the gate. So we can assume that the height of the gasoline is 4 meters. We still don't know what force we're getting from the left-hand side because we don't know H just yet, and we're going to solve for that. All right, before we do that, let me get, I'll go to the next slide, and we've got an iClicker question. So go ahead and get your iClickers going. I need to step out of the show to bring up our iClicker app. I wasn't prepared for that, I guess, today. There we go. There it is. Okay, and then let me get it's taking a little second here to get going. Maybe because it's so cold outside. All right. Start class. Okay. There we go. So there's our app. Let's pull this over. I'll move it back here in just a second. Okay. So the question that I have for you then is just a gut check. Okay. There is a right answer to this, but let's just think about sort of what makes the most sense here. Before we solve this problem, what do you expect? Do you expect that to satisfy the question, which is at what H do we, on the left-hand side, the height of water, do we start to open this up a little bit, this gate, so it starts moving to the right? Will that mean that H needs to be between A is really, oops, sorry, go back. Somehow my pen got turned off. A is meant to be sort of from here to here. B is indicating from here to here. And then C is up in this region here. Okay, so I'll get the clicker going here, but the iClicker quiz or input. All right, so we'll go for a minute here. But you just have to choose one of these, and we'll talk through the solution here by the end. So should H end up being half the height of the gasoline, somewhere between half and full height of the gasoline, or should it be greater than the height of the gasoline? And really, we're just looking for that point where FR water, right? So this is coming from the left, versus is overtaking or is just equal to FR gas, so the resultant force from the gasoline side. So that's the force balance. I'm sort of giving that away, I guess, a little bit. But when we work through this problem, you'll see how we're going to solve for H. All right. 80 responses. We'll have another poll, by the way, at the end of the lecture materials, too. All right, we're up to 90. How many folks do we have? Oh, I see. Need to move that as well. Well, fully. Huh. Okay, let's go ahead and stop and take a look. All right, so 11 of you said A, that we would have a fairly low height of water. B was the most popular, so somewhere between halfway up H1 and all of H1. 59 of you said that, and then 24 of you responded that H would need to be greater than H1. Okay, let's leave this alone for a second, and we'll come back to this answer after we solve the problem. But I don't want to give it away just yet, so let me minimize that and put it off to the side for a moment, and we'll come back to it. All right. Okay, I've set this up so that we kind of step our way through this question. And so I've broken it up into a lot of really simple pieces. So the first piece is, what is the specific weight of the gasoline? Well, now this will help us because we know that eventually we're going to need to calculate the resultant force due to the gasoline on the right-hand side. And we'll also, let me not draw that at the exact same location, but somewhere we will also have to, and I've arbitrarily drawn these lines. I just wanted to make sure they didn't line up in space because we don't know that yet. Sorry, not FG. This would be FW. FRW. FR. The resultant force due to water versus the resultant force due to gasoline. Okay, so let's start with the specific weight of the gasoline. So we said we're going to call gamma water 9810 newtons per meter cubed. And so the specific weight of the gasoline in this case, we said is equal to the density of the gasoline times G, right? So we said that this was 700 kilograms per meter cubed. And when we multiply that density by the acceleration due to gravity, so 9.81 meters per second squared, we end up with a value of 68, oops, sorry, need an equal sign in there, 6870 newtons per meter cubed, okay? All right, so that's a good start, and it's something we're probably going to need. Now, I'm leading you a little bit here, but the next question is, what is the force of the gasoline on the vertical plane? And we've used this equation over the past few classes to say that our resultant force, in this case of the gasoline, is going to be equal to gamma gas times the centroid height of the gas times the area of the gas interacting with the gate. Okay, so this is why ultimately we needed the specific weight of the gasoline. Okay, so if we work this out, we get 6870. We said newtons per meter cubed. We're going to multiply that by HC. Okay. In this case now, we said that H1, this whole height, is equal to 4 meters. And because we have the pressure increasing linearly with depth, we can basically take 1/2 that. So in other words, HC gasoline is equal to our H1 in this case over 2. So this ends up being 4 meters of total height of gasoline divided by 2 gives us 2 meters. Okay, so our 2 meter centroid location of pressure, and then we multiply by the area of the gate that is in contact with the gasoline. And so that's going to be 4 meters high times 2 meters wide. Okay. When we multiply this out, we end up with FRG being equal to 110 times 10 to the third newtons, or 110 newtons. Kilonewtons. Okay. So that's the right hand side of this, and of course, as we've drawn this, I guess this step that I skipped was to write this force balance. But whatever H needs to be on the left hand side, we'll have to create a resultant force of the water hydrostatic pressure on the left hand side that would counter that of the gasoline on the right hand side. So that is our step toward figuring out the right hand side of this. All right. Just make sure everybody gets out. I'll give you another couple of seconds before I advance. Part C now is going to be to start asking about these lines of action. Where does the resultant force occur with respect to the hinge, particularly for the gasoline? All right, so in this case now, we know that we have some FRG here, and I'm going to call this height here, its location, L sub G. Okay, so it's some length or some height above the bottom of the gate or the hinge that will give us this value. Now, remember that I'm going to write an expression for L sub, that's weird, it should have been an equal sign, for L sub G that basically says, remember that I'm just going to jump back for a second, 3 slides. Oh, no, a little more. Here we go. Remember that when we're dealing with these y's, the y sub r, the y sub c, those are distances that are measured outside of the gate or along the plane of interest, right? So whether it's a gate or a wall or what have you. And so what I need to do with L sub G is to say, okay, this is going to be the height above the hinge, but I'm going to set that up as being H1 minus y sub r g, right? So there's a y sub r that is the resultant force line of action or distance along the gate that FRG is going to act on, but it's measured from the top down, not from the bottom up. Okay, and that's why, so this is going to be equal to 4 meters in this case minus YRG. Okay, so we have to figure out the resultant force of G, this Y distance, so that we can do this math, all right, to just look at the difference from, or the distance up from the bottom rather than from the top. Okay, so YRG is going to be equal to, this is our customary equation, right? We said Y sub C for the gas plus the moment of inertia IXC for the gas divided by YCG times AG, right? And if we go to our equation for our set of equations for the different shapes for our moment of inertia, we're going to note a couple of things. One is the center of gravity, in this case, this Y sub C, is going to be equal to 2 meters, right? That's the center of our, the center height, in this case, the Y dimension for our gate, because it's only filled to 4 meters. Then we're going to add, this case, this was the second thing we would find, XC is equal to 1/12 times the width times the height cubed. And that's 4 meters. Okay, and then we divide that by y sub cg was 2 meters, and then we multiply in the denominator by the area, 4 meters times 2 meter height, right? And ultimately we've got this 2 meters will cancel with this one, this 4 will cancel with these to make a 2, and we can basically work out this math. And when we do, we end up with YRG being equal to 2.67 meters. So in other words, this 2 meters was most of the way down. That's our y sub c. Pardon me. We added another 2/3 of a meter essentially to get down to that location where FR acts. Okay. So, but remember, the question was with respect to the hinge, right? So L sub G is equal to 4 meters minus 2.67 meters. That equals 1.33 meters. Okay. Now, if we were working with our significant figures, we would, there's a lot of these that are one significant figure, a lot of terms that we've used to this point in this part. So we would probably change that to 1 meter, even though that wouldn't be quite the right location. It's the limit that we have for the numbers that we were given to put into this. All right. What is the moment of force? Although I would argue, as we've tried to reinforce, you can wait until the very end to work on your significant figure. So if that was all we were asking for, that would be fine. But we're going to keep going with this because we still need to figure out what H is. We haven't figured that out yet. So what is the moment of force of the gasoline about the hinge? This is setting us up for thinking about the sum of the moments about the hinge that are going to be acting in opposite directions, right? We know that this has to equal 0, and we're going to have one moment acting from the FR of the resultant force of the water, the other one from the gasoline. But right now, this is just asking about the gasoline. So we would have the moment due to the gasoline is equal to FRG times LG, right? It's a force acting to the left and perpendicular distance up to that to that force ends up being 1.33 meters. So we end up with 110 kilonewtons times 1.33 meters gives us 1 point, actually, yeah, 1 point, nope, I need to get rid of that point, sorry. 146.3 kilonewtons, kilonewton meters, okay? Now, there's a reason I wrote it this way, which is not kind of our standard 3 decimal place or 3 significant figure scientific notation, and I'll show you that in a second as to why we did that. I almost said moment, wanted to make a joke, but let's not do that. So, so there's our moment right there. That's just due to the gasoline hydrostatic force. On the next slide, we're going to have to put together the full equilibrium so that we can solve for H. So I don't have any more of like parts E and F and so forth. The next part is we've got a bunch of the pieces. Let's put the whole story together. So on this slide now, we're going to start with the sum of the moments about H equal to 0. And that's going to be equal to, let's see which one's acting in the positive direction. I'm going to say F RG LG, a value we've already calculated, minus FRW LW. So we don't know how much FRW is yet or how high up it acts because we don't know what H is yet. All right. So the first thing we can do is we do know these two. So we can solve for at least a magnitude on the left-hand side. So FRW is equal to, on the left-hand side, we can just solve for this first piece. we say this is gamma W, so the specific weight of water times H, the centroid height or depth for the water side, times the area of that water interacting. When we work this out, we're going to get this in terms of H. 9810 newtons per meter cubed times H over 2, whatever H is going to be, times H times 2 meters, right? So what that means then is that we end up with, these 2's end up canceling with each other. So we end up with FRW is equal to 9810 10 newtons per meter squared times H squared. Sorry, this should just be newtons per meter, because we're going to multiply it by this length squared. Okay, so that's part of the way there. Ultimately, we could probably find another way to represent LW in terms of H so that we can just solve for H, and that's what we'll do now. So LW is equal to, just like we did before, H minus YRW. So this is now equal to, I'm just going to keep all of these together, this H minus, and then we've got Y sub C, the centroid length to the water on the left-hand side of the gate, plus IXC water divided by Y C of the water times the area of the water interacting with the gate. And this now becomes equal to H times, so minus H over 2 is our center of our distance to the centroid, plus 1/12, and now we have the times the width, which is 2 meters, times the height H, which is cubed, and then we divide by H over 2 for our Y sub C, and H times 2 meters for our area. Okay. Again, we've got some simplification that can occur here, but ultimately all of this stuff in these brackets boils down to LW being equal to H minus 2H over 3. Okay. So all of the combining of the fractions on that big equation basically boil down to that. And that turns out to be what? Basically 3H over 3H minus 2H. 3H over 3 minus 2H over 3 equals H over 3. Okay.
How is the H over 2 determined?
This value here is the distance to the centroid, because we're going to end up with a pressure that looks like this. And so to figure out our centroid, it's always for the pressure, it's always at the middle of this square to get to the centroid. Okay. The force doesn't act there. That's just where the centroid of the area is. The force acts at Y sub C, the centroid, plus this other term to give us our Y sub R.
I thought the centroid was the midpoint of the gate.
The midpoint of the height. Yep. But it's only where the water is interacting.
Okay. So that's the centroid of the gate with respect to the water.
Yeah. And okay. I was trying to be very careful. So the YRW is different than YR gas G.
Okay, I have a follow-up question with that. How would it be different if the gate weren't like a rectangle?
Well, then you would use a different equation here, going back to that figure.
Would the H over 2 also change?
No, because pressure still should act
Just halfway down.
Increase, yeah.
Okay, thank you.
Yep.
Okay. One more question. Sorry.
Yep.
For the units for FRW, how did you go from the newtons over meter cubed to newtons over meters?
Oh, we're not done yet, because we don't know what H is, but H is going to be squared. So it should be squared, shouldn't it?
Okay.
Yeah, I'm sorry, you're right. So let's see. It has to come out to newtons. So I was trying to be quick here, and I didn't. I should have trusted my notes. This should be newtons per meter squared because this meter canceled with one of those and left two behind.
Yeah.
Thank you.
Okay, well, thank you.
So when we have h, whatever length it is, in meters squared, it will work that out. Okay. So now.
And so, really quick, LW is the distance from the bottom of the tank to where the force, the pressure force of the water is acting on the gate.
Yeah. So let me change my pen here. So if this is FRW, this height, I realize that's a little hard to see. It's kind of jammed in there, is LW. Yeah. Versus LG working on the other side, the gasoline side. Does that make sense?
Yeah.
For some reason I can go backwards with my arrow keys, but I can't seem to advance. Okay. So finally then, I'll go back to red if I can. All right, there we go. Red here. Okay, so now 9810 newtons per meter squared times h squared. And if I go back up to this very top, my LW I multiply by is now h over 3. So times h over 3 is equal to 146.3 kilonewton meters. So if I work this out, I solve for h being equal to 3.55 meters. Okay? So the first clicker question we had was about just roughly how high should in an approximate way, how high should the water be on the left-hand side of the gate? Should it be between 0 and 2 meters, 2 and 4, or greater than 4 to get that to basically come up with this force balance? And it turns out the answer is 3.55. So if I just go back to that question that we asked, it turns out that B was the right answer, right? Because we ended up with 3.55, which is what, somewhere, oh, actually, sorry, that's not right. It's somewhere kind of up here-ish, right? But part of the reason that those two hydrostatic forces are different from each other is because the gammas are different, right? You put water on one side, water on the other, well, then it just depends on which one's higher as to whether it's going to open or not, right? But when it comes to gasoline, which had a lower density and therefore a lower specific gravity, we now have an imbalance. So it doesn't take as much water to offset the FR from the gas because it has a higher specific weight. I think I said gravity earlier, I meant specific weight.
I have a quick question. So when you're determining LG, since pressure just varies like linearly with depth, could you just multiply the height times 1/3 to find where LG is?
Cole, that is a perfect transition to pressure prisms. So that answer I'll give you that answer in just a moment. But before we do that real quick, is one thing I guess I've noticed here. I thought for some reason I was including I needed to keep everything in kilonewtons. I think that was for a different problem I was working. So my apologies. You do note that when you solve for this, you'll have to convert either the right side to newtons or the left side to kilonewtons to get this to work out. But you should still come out with about somewhere in the order of 3.5 meters to solve for H. Okay. So now let's talk about this concept of pressure prisms. And Cole, this basically gets to the question that you were asking. You had picked up the pattern that there's this 1/3 height for the centroid of the pressure. And that turns out to be the core of this pressure prism concept. That essentially we can, let's see, that goes over there. That we can look at this pressure and its shape, right? It has this triangular shape, but it starts at 0 as a gauge pressure and then goes up to some high value down at the very bottom. And it's a linear change because all of this is the same specific weight, whatever it is. If it's water, that's for water, what have you. Okay, so F sub r, as it turns out, one of the ways that we can assess the this force is to calculate the volume of this prism. Okay, because integrating all of that pressure over an area gives you a force, right? So in this case, we're gonna work this out. The way this would look for this triangular prism is we would say 1/2 times gamma h, right? So that's this left hand, or on the other side, the right hand side, that's the area of the triangle, right? And then we multiply by, in this case, b times h, where b, notice, is the face. So b is sort of on the left hand side, b is going into the plane here. On the right hand side, you can see we've kind of tilted this a little bit with a 3D view. B is the width of the wall or the gate or whatever the left-hand side vertical plane is. So this is the area of the plane, and this is the, is this the area? No, this is giving us, this is the, what's the right way to put this? I guess this is half of the magnitude. I can't, I didn't write this out before, and I'm a little concerned about writing it out now. But essentially, you can see that what we're getting is half of this sort of integrated pressure on the left-hand side, or on the side of this prism, multiplied by the front area of the prism. So this would come out to be gamma h over 2 times A. Right? Now, h is going to be built into A, we expect, the height of this prism. So you could also write this as gamma h squared b over 2 or something like that for a rectangle. All right? Now, to get back to what Cole was specifically asking, though, FR acts, as it turns out, at the centroid of the prism. Centroid of the prism, not the centroid of the area that fluid is interacting with. So the centroid of the prism, as it turns out, is always this h over 3 from the bottom, or 2h over 3 from the top, right? So Cole, it was a good thing you picked up on that. But what I do want to do on the next slide is actually prove this to ourselves. So we're going to work through just one example of where we would take this same idea, which we've done before, and I just want to demonstrate where this comes from. Okay. So on one level, you can trust me. On another level, let's just make sure we're right. Now, this works for rectangles where b times h is either a square or a rectangle on the interface. It doesn't necessarily work for, in the same way for, say, a triangle or a circle where that interface is occurring. But it would if you integrated over that area. So it's best for these rectangular areas for the pressure prism. All right, let's prove this to ourselves real quick. So what I want to do is recall that we said that essentially what we're saying, that the shortcut is that we have said that, there's some h minus yr is equal to h over 3, right? That's more or less what we wrote on the previous slide. We just didn't do it quite so succinctly. So recall that when we did this sort of the longer way, we said yr is equal to the y sub c plus I xc over y sub c times a, right? And when we have a rectangle, when we have a rectangle, we know that we have, sorry, not h, y sub c is equal to h over 2. So that's the y location of the centroid. And we know that the area, of course, is h times b, right? So y sub r, that distance to the location of the action of the force, F sub r, is equal to h over 2 plus 1/12, and this was times the width b times the height h to the third power divided by h over 2 times the area b times h. Now here's the deal. We can now cancel out these b's. We can cancel out 2 of these h's from the numerator. And what we end up with is h over 2 plus 2 over 12 times h. Yeah, I thought I'd have more in the denominator. 2 over 12. So ultimately, then if we simplify this, we get yr is equal to, I'm going to put it all in terms of sixths. So can I do that? Yeah. So we would say 3h over 6 is our h over 2 plus 1 over, 1h over 6 equals 4h over 6, which is basically equal to 2/3 h. Sorry, that's a little, I was going to try to put h next to it, but I kind of goofed that up. So y sub r is equal to 2/3 h. So L, measuring up from the bottom, is always 1/3. Okay? So pressure prisms are really handy because we make use of this repeated geometry over and over, where a rectangle is on one side and it has a triangular side shape to it, and so we can work through that. So let's talk a little bit more about pressure prisms in general. We can start to think a little bit about whether. Oops, I guess I gave myself an extra slide there, which I didn't use. All right, so can we use pressure prisms for deep pressures? That is to say, like somewhere way below the surface, I have a gate that I need to worry about. And if we do, the answer is yes, we can, but we need to sort of think about the shape of that prism before we do it. The shape of the prism that we care about for this case now looks like this, not like the triangular one that we looked at before. Right? Now we basically have a trapezoid kind of on its side. And we can break that up into 2 pieces. One piece is a rectangle, and we can solve for that. And the other piece is this triangle, which is the pressure prism like we looked at on the previous slides. Okay? So the rectangular part is essentially due, you can think of it as an offset. It's due to overlying pressure. Right? So in this case, this H1 times gamma, that is right here. That whole rectangle has one dimension. The top and bottom dimension is gamma H1, and then its height is whatever this H1 minus H2 is, right? Whatever that value is. The triangular piece is, like we showed before, due to the fluid, FLUID, okay, that is directly interacting with, I would say, our, it's supposed to be an N, with our, what I'll just call plane of interest, right? So it could be a gate, could be a window or something like that. So the beauty of the rectangular part of this is it provides the offset for the overlying pressure to get down to a depth that we start to care about. Then we increase pressure with our typical triangular pressure prism, and then we add those two together. Okay, so to get our full pressure or full force acting on the right-hand side. Now, note also, FR would be the total force, and we can break this up into two pieces. We can figure out F1 acting at the middle of our rectangular part of this pressure prism, and F2 acting on the triangular part. Okay, what we talked about a slide or two ago is that we know F2 is going to act 1/3 up from the bottom. F1, on the other hand, is going to work right in the center. And the reason is that is just a rectangle. All right, it's a rectangular face probably on the right-hand side. We don't know anything about the depth necessarily, or the width into the board here. But that rectangular prism will have a line of action that works through its centroid because it's not changing with depth. Okay. Okay, what about a non-vertical planar surface? Can we use pressure prisms there? If we look at the shape, again, it's not a triangle anymore. Once again, we have a trapezoid. And once again, now this is again buried, so to speak. This plane of interest is some H1, the top of it is H1 deep underneath our surface. So once again, we can say, yes, we have this rectangle, right, as part of the pressure prism, and its height here is equal to gamma times H1 all the way down. Then we have this triangular piece that is increasing with depth, okay? So once again, yes, we can do this. That's not a problem. We can basically evaluate the rectangular part of the prism just like we did on the vertical face, and we can evaluate the triangular part of the prism. Now, if this non-vertical plane that we cared about came all the way up to the surface, then we might also, we would start at 0. We wouldn't have that rectangular piece. So we could still, basically, all this means is, yes, we can rotate a triangle and deal with it, or we can rotate a trapezoid and work with it as well. All right. So what about for these deep pressures, or for absolute pressures, rather? Absolute pressures we're going to treat as if we had sort of deep planes that we care about. So the fluid itself, if we look at the left-hand side, creates this pressure prism, right? This triangle that we've talked about already from the side. In the front, it's got some rectangular area to it. The atmospheric pressure will add a constant offset to these pressures through the depth, as if I'm saying department, that should be the depth of the fluid. And so essentially what we show is that we can take all of our values and offset them by P atmospheric, or add P atmospheric to them to get the full force if we were putting this in absolute pressures instead of gauge. So, however, we tend to kind of ignore this. And the reason is that the fluid pressure is acting obviously on the fluid side, but on the outside of our domain, whatever it is, a reservoir or something, we have the same atmospheric pressure acting over there. So the two of those are canceling each other out. So we often don't care about doing this in an absolute pressure way because we have atmospheric pressure working on the left-hand side and the right-hand side, and they, from a physics perspective, they cancel each other out. Oops. Is there anything else on that? Don't think so. Okay. All right, here's example 2.8 from your book, and I just wanted to walk through it because it provides us with a really nice example of how to put all of this together. So let's talk about, there's a tank here with that's partially filled with oil, And then on the side of this tank, there's this plate that's bolted into place, okay? So a pressurized tank contains oil that has a specific gravity of 0.9, so it's less dense than water. And it has a square 60 centimeter by 60 centimeter plate bolted onto the side. The pressure gauge at the top of the tank reads 50 kilopascal, okay? So that's the air above the oil. And the outside of the tank is at atmospheric pressure. So the question is, what is the magnitude and direction, or location, pardon me, of the resultant force on the attached plate? All right, so we could think about this maybe as a patch, right, in our tank. For some reason, there was a hole there. We cut out this 60 centimeter by 60 centimeter area, and we put this plate in place to patch that hole, so to speak. All right, so let's just take, on the right-hand side, let's take the plate and think about what's occurring here. The plate starts at a depth of 2 meters below the surface of the oil, and it's 0.6 meters tall, right? So the center of that is 0.3 meters, but it's ultimately 2.3 meters down from the oil surface, right? So this is 2.3 meters. To get all the way down to the bottom, we have to go 2.6 meters, right? 2 meters to get to the top of the plate, and then another 0.6 to get down to the very bottom. Now, there is going to be some location, we expect, where FR is acting. I kind of wish I hadn't done that. I wonder if I hit undo that? No, I can't. Okay, sorry. I've got another piece of this that's going to come in. So there's my extra arrow. Sorry about that. Now we can now look at this like it is a trapezoid. All right, and the trapezoid has 2 pieces to it. One piece is what looks fairly square, but let's just call it rectangular here. And all of that pressure prism is due to that 50 kilopascal in the air above the oil. Okay, so that pressure is added to anything that's inside of that tank. And then after we go below the oil, we have that pressure plus the hydrostatic pressure of the oil building up above us. So the hydrostatic pressure of the oil building up above us is this. Actually, I'd forgotten there is one more thing that this does, which is not only do we have the air pressure up there, we also have the height of all of this oil bearing down on us, right? The hydrostatic pressure of that 2 meters of oil before we get down to the patch to begin with. So there's actually 2 pieces to that square or rectangular part of our pressure prism. All right, so let's go through and talk about how to calculate this. First, we're going to consider that we have forces, 2 forces that make up FR. So FR is equal to an F1 and an F2, where F1 is our F1 is going to be the rectangle. Air pressure in the tank, and what I forgot to add, and overlying oil. So there's that. Then F2 is just due to the oil pressure as it changes, the hydrostatic oil pressure as it changes over the face of the what do you call it, our plate there. Okay. All right, so let's take F1 first and consider it. F1 is equal to, we're going to have the pressure inside of the tank. I'm just going to call this P. Well, maybe let's call it P tank. So this is going to be P tank. And then we add the overlying oil, so gamma oil times H1, and then we multiply that by A, the area of our plate that's interacting, okay? These are all constants. There's nothing changing with depth. In this case, it's just, well, it's not changing with depth because we have a fixed perspective here, okay? So if we calculate this, we would end up with 50 times 10 to the third newtons per meter squared plus 0.9 times 9.81. Did I write that? Oh, I see. Okay. Times 10 to the third newtons per meter cubed. And then times H1, which is 2 meters to get down to the top of our plate. And then we multiply by 0.6 meters and we square that. Okay. And that is the 0.6 by 0.6 is the area of the plate itself. Okay. So when we work this math out, we end up with 24.4 times 10 to the third newtons, or 24.4 kilonewtons. Now, this case, this is the one I was remembering. We want to keep this in 10 to the third newtons, and I will, because when we calculate F2, we'll just look at the comparisons of those two values, okay? So there's F1, and that is all of our overlying pressure from the air pressure in the tank and the hydrostatic pressure to get down that 2 meters of oil till we get to the plate. Okay, so now let's calculate F2. I have enough room for this, so we'll do this. F2 is equal to, now we're going to have gamma oil, right, times, and now we have, I'm going to write this in terms of H2 minus H1 to get to the centroid of the center height of the patch or the plate, and then times A. Now, we know that this difference is 0.6 meters, but I wanted to illustrate that it's 2.6 minus 2 to get to that location within the height of the tank. So now we have, we said we have 0.9 for our oil times 9.81 times 10 to the third newtons per meter cubed, and then we multiply that by 0.6 meters over 2, and then the one thing I couldn't quite squeeze in there is now we multiply it by the area, which is 0.6 meters quantity squared, right? So when we work this out, now we end up with F2 being a value of 0.954 times 10 to the third newtons. Okay, so before we go any further, just take a look at those two magnitudes. The additional pressure or force that is added by the pressure change over that 0.6 meters is less than 1 times 10 to the third newtons, whereas all of that air pressure plus the pressurized situation inside the tank plus the overlying 2 meters gave us 24.4, right? So those are big differences in the two magnitudes there. Okay, I want to go to the next slide and figure out our resultant force total. Well, actually, let's just do it here. The total resultant force, FR, then, when we add these two together, because they're acting in the same direction, is equal to basically 25.4 times 10 to the third newtons. Okay? Sorry, I don't know why my zeros are so bad. I guess I write them too quickly. But there's our total force now acting on this plate. All right, so where does it act? It turns out F2 acts in one place and F1 acts in another, right? Here's F1 acting at the midpoint, so 0.3 meters up from the bottom, 0.3 meters down from above. That's because it is a rectangle. But our triangular pressure prism over here that has F2 associated with it acts 1/3 of the way up, okay? So it is acting at 0.2 meters above the bottom. Now, what we're going to do is try to figure out where FR as a total actually acts. So we have to add these two vectors together and figure out where they act. So let's do that on the next slide. We note that F1 acts at the center of the window, or sorry, center of the plate. So I'm going to call this y F1 is equal to 0.3 meters from the bottom of plate. And F2, 2 acts at 1/3 of plate height. So in other words, YF2 is equal to 0.2 meters from bottom of plate. Okay, so now we can add these together by basically summing the moments. So the moment due to FR of, I'm just going to call it Y0, which is what's noted here. It's Y0. So that's where FR is acting. And to get that value, we know what FR is, but we need to basically weight this by F1 times Y F1 plus F2 times Y F2. Right, so this now, if we solve for Y0 or Y naught, this would be equal to F1 F1 plus F2 YF2 divided by FR. So this comes out to be 24.4 kilonewtons times, times 0.3 meters plus 0.954 kilonewtons times 0.2 meters divided by that total, which was 25.4 kilonewtons, so that Y naught comes out to be 0.296 meters, or about 30 centimeters up above the bottom of the plate. Okay. All right, the last thing I have is one more clicker slide. So after you guys get done writing that out, you can see, by the way, that the total FR is acting kind of halfway, or not halfway, but at a midpoint, somewhere between 20 centimeters and 30 centimeters, right? Obviously closer to the 30 centimeters because F1 is so much bigger than F2, right? It's kind of weighting those two distances. All right, here is the question. Ugh, this looks ugly. Let's talk it through real quick. We've got a couple minutes. For this right angle gate, so you can see the dark gray is indicating a right angle gate here. It has a single hinge at O. How would we calculate the effective force on the horizontal piece? All right, the way this works is that at some point when you raise water high enough, you will create a big enough force over here that will tip this over so that you start putting water down this pipe. Okay, that's the way this is supposed to work. So it's kind of like a little check dam, sort of, or check gate, I guess, for that matter. Okay, so let's take three options here. Should the downward force that is acting on this plate be equal to gamma water? We're given that it's water. Gamma water times, I'm going to assume that the B is the width of the gate into the page here. So is it gamma W times H times L times B, and I'm going to call this length here L. We're not given its actual length. Is it gamma W times H over 2 times L times B, or is it gamma W times H times pi over 4 times diameter squared of this pipe? All right, so let me get this started. Oops. And go. All right, so we'll get a minute for you guys to think about this. Which of these three is the correct value, or the correct equation that we would use?
How does the gate actually open again?
So when you build up enough H, you basically build up this resistance force so that this pops down and water starts going into the pipe. Okay, how we doing? Got another 15 seconds or so. I suppose we have 97 folks involved, so we should probably have about 94 responses. All right, and there we are. Okay, so let's go ahead and end that at 1 minute. Great, and let's take a look at the results. Okay, so we've got A, B, C. B seems to be the most popular, but it's only closely outvoted by or outvoting A, and then we've got C. Okay, when we talk about FR and the pressure that is acting, let me change the color of my ink here. Come on, I'll go with blue. Okay, pressure, remember, is acting at the top and bottom of this horizontal plane. And this is the first time we've seen this. So, don't worry about having gotten this wrong. But I just want to remind you, I just want to go back to the basics. The pressure is acting the same in all directions at the same elevation. And so if this isn't, we'll have to think about this as being infinitesimally thin gate, then the pressure force from the top and the bottom is offsetting each other. All right. Which means that F down, I guess technically you would consider that, but you might also consider the up part, which is not included here. So really, I maybe should have said this, the net downward force, but this one is wrong because it's not the net downward force in and of itself. We have this other pressure force acting up from the bottom, which is offsetting everywhere with the exception of the location over the pipe. Where the pipe occurs, you don't have an upward force, you only have a downward force occurring. And so you would just work within sort of that range, that width in this case. A little bit of a trick question. I just wanted you guys to think through it. We won't put that one, on the exam or anything or on the homework, but I just wanted to get you guys to think through that a little bit. Okay, so quick wrap up for the day. Homework 4 is posted. It's due on Thursday. Emma will have office hours tomorrow morning, her usual time. I will have office hours tomorrow afternoon at my usual time, and I'll be happy to answer some questions if you have them, but I do have to get back to a National Academies meeting that I left to come and teach. So have a great afternoon. It was great to see you all, and I'll look forward to seeing you on Thursday. Take care.
Thank you.
Thank you.
Thanks. Thank you.
Thank you.
I had a quick question about what the format of the test is going to look like.